There are rules that govern the entire universe. I mean, everything, from the biggest stars right down to the smallest atoms. They're the reason engines run, why ice melts, and they're even the reason you exist. So let's dive in and see how a simple cup of coffee can unlock the laws of everything. All right, so our journey starts with something we all know, right? A hot cup of coffee. Let's say it's about 70 degrees Celsius, and it's just sitting in a room that's a nice, cool 20 degrees. We've all seen this a million times. But have you ever, really stopped to think about what's actually going on here? It's such a simple question, but the answer is incredibly deep. Why does the coffee always get cold? Why does the heat flow from the cup into the room and never ever the other way? I mean, think about it. Why doesn't the cool air in the room just decide to gather all its energy together and make your lukewarm coffee hot again? The answer, it turns out, is in the laws of thermodynamics. To really get to the bottom of this whole thing, we've got to start thinking like a physicist. And that means we're going to treat this little coffee cup like it's our own personal universe. So let's lay down some basic terms first, just so we're all on the same page. First up, we've got this idea of a system. It sounds fancy, but in thermodynamics, a system is just whatever part of the universe we decide to focus on. That's it. For us, the system is the hot coffee inside the cup. Everything else, the cup itself, the table, the air in the room, you, me, that's all called the surroundings. Simple, right? And what's so cool is how universal this idea is. It doesn't matter if it's just a shape we draw on a whiteboard or the actual gas trapped inside the piston of a car engine, the principle is exactly the same. We just draw a line, real or imaginary, and say, okay, this is the thing we're studying. It's the very first step to understanding how energy moves around. Now, this slide here is great because it breaks down the different types of systems, and it uses our coffee to do it. So just sitting there steaming in the open air, it's an open system. Why? Because both heat and mass, the steam itself, can escape. Now, if we pop a lid on it, it becomes a closed system. Heat can still get out through the walls of the cup, but the water vapor is trapped. And the whole point of a fancy thermos? To create an isolated system, trying to stop any heat or mass from getting in or out. So we have our system, we know what we're looking at, now we need the rules of the game. And the laws of thermodynamics? Well, they are the absolute, non-negotiable rules for how energy works. Everywhere, all the time, no exceptions. We actually start with a law that's so fundamental they had to go back and call it the zeroth law. Seriously, you can just think of it as the thermometer rule. All it says is that if two things, A and B, are each the same temperature as a third thing, C, well then A and B are the same temperature as each other. It sounds totally obvious, I know, but that simple fact is the entire reason thermometers can even exist. It's what gives us a consistent way to measure temperature. Okay, let's move on to the first law. You can pretty much sum this one up with a famous saying, there's no such thing as a free lunch. This is basically the universe's great accounting principle. What the first law really states is that the total amount of energy in an isolated system is constant. You can't just create it out of thin air, and you can't make it disappear. All you can ever do is change it from one form to another. Think about it. The chemical energy in fuel becomes the kinetic energy that moved your car, and that becomes heat energy in the brakes when you stop. The energy just changes hats. And because of this law, a whole category of dream machines becomes instantly impossible. This is what's called a perpetual motion machine of the first kind, a PMMI. It's a hypothetical device that could just keep doing work forever without any energy being put into it. The first law looks at that idea and just gives a hard nope. You can't get more out than you put in. The cosmic books always have to balance. So the first law tells us we can't win. But the second law? The second law is the one that tells us we can't even break even. This is the law that gives a direction to time and a direction to the flow of energy. It's the cosmic tax, and it's the law that's finally going to answer our coffee question. The second law is so important that it actually has a couple of famous ways of being stated. They sound different at first, but they're really just two sides of the same coin. The Kelvin-Planck statement is all about how engines work, turning heat into work. And the Clausius statement is about how refrigerators work, moving heat from a cold place to a hot place. So let's look at the engine side of things first, the Kelvin-Planck statement. Here is the absolute dream, right? A perfect engine. It takes in 100 units of heat from some hot source, and it perfectly converts it into 100 units of useful work. Zero waste, 100% efficiency. The second law says this is impossible. And here's the reality. For a heat engine to do any work at all, it must have a hot place to draw energy from and a cold place to dump waste heat into.
It takes heat from the hot source, turns some of it into work, and is forced to dump the rest as waste heat into that cold sink. That waste heat, that's the cosmic tax. And that is why your coffee gets cold. Your coffee is the hot source, the room is the cold sink, and the heat must flow, always from hot to cold.
Now let's flip to the other side of the coin, the Clausius statement. Here's the refrigeration dream, a magic box. It just sits there, sucks all the heat out of the cold space inside, and dumps it into the warmer room, all by itself. No plug, no power, nothing. It would be heat just deciding to flow uphill from cold to hot for free. And you guessed it, here's the reality check. The second law says that heat will not flow from cold to hot spontaneously. It just won't happen. If you want to force it to go that way, against its natural direction, you have to pay. You have to put work into the system. That's exactly what the compressor in your fridge is doing, and that's why you have to plug it into the wall. You are paying the electricity bill to fight against the natural flow of heat. And this is not just some abstract theory in a textbook, okay? These laws are literally the blueprints for our entire modern world. They were absolutely everywhere. I mean, just think about where your electricity comes from. A power plant is just a gigantic heat engine. It burns fuel to create a super hot source, uses that heat to spin turbines and do work, which is the electricity, and then it has to dump all that leftover waste heat into a cold sink, like a river or the atmosphere. And your air conditioner, your fridge, they're just everyday heat pumps. They are living examples of that Clausius statement. They use electricity to do the work of pumping heat out of your cool house and dumping it into the already hot air outside. They're in a constant battle, pushing heat uphill to keep you comfortable.
And then you've got these incredible marvels of engineering, like a jet engine. It's just a brutally powerful heat engine. It takes the chemical energy from fuel, turns it into mind-boggling amounts of heat and pressure, and directs all that energy to do an insane amount of work in the form of thrust that pushes a massive airplane through the sky. So look how far we've come. We started with a simple, cooling cup of coffee, and we've ended up with the engines that power our entire civilization. So let's just zoom out one last time and see how truly universal and how deeply personal these laws really are. Because here's the thing. It gets even more personal. You are also a thermodynamic system. You are an unbelievably complex, highly ordered collection of matter. You take in energy, food, and you use it to do the constant work of just living, maintaining your body temperature, building new cells, and constantly fighting against the second law's relentless push toward chaos and decay. You see, the second law tells us that the universe's arrow of time points in one direction, toward more randomness, more disorder, more chaos. And yet, here we are, pockets of incredible, beautiful order and complexity. So what does that make life? Well, maybe it's the universe's most beautiful rebellion against its own rules.